In this video, we're going to be looking at big numbers on atomic structure. And so, first is we have this question which says that the Ba2 plus ion has how many electrons? And so, looking at this here, there is a specific symbol that we need to keep in mind, which is a chemical symbol representing Ba, and Ba represents the element which is beryllium. And looking at beryllium on the periodic table, you'll observe that it has its atomic number to be 56. 56, what does that mean? This means that you have the number of protons, which is that exact number, as that of the number of electrons. That is why that atom here, in this case beryllium, is neutral. And so in this neutral state, the number of protons, positive charge, and the number of electrons, negative charge, are the same. But in this case here, for this question, we notice that we are going from beryllium, which is its neutral form, and is going to be losing what? How many electrons here? 2 electrons, because the oxidation number here is 2 plus. And so what that means is that when you do the math problem here, that means that starting at the number which is 56 for the neutral state, it loses 2 electrons, and that results in 56 minus 2, which gives you what? 54 as the number of electrons that is present in beryllium 2 plus ion. So now, in addition, take note that when you look at the oxidation number for each of the species in this half equation, you need to realize that for a neutral atom, it's going to have an oxidation number to be what? 0. And once you have that, take note that the sum of the oxidation numbers on the left side of the equal sign, or the equation arrow, must be equal to the sum of the oxidation number on the right side of the arrow. Therefore, in this case here, 2 plus negative 2, this here will give you 0. That is on the left side of the equation. Now, once we have this, next is how about you're given a question that is in this particular format, which says that what is the maximum number of electrons in the principal quantum number 3? And so to address this question here, we need to know what the principal quantum number 3 represents. This here is represented as the variable, which is n, which is the principal quantum number, the first, take note, quantum number out of the 4 quantum numbers we have, and this here is equal to the number 3. Now what that means now is that when it comes to what is the maximum number of electrons in that principal quantum number, we need to know what the expression is, and the expression here can be determined by 2 multiply the n to the power of 2. So in this case here, once we recognize this expression, we're going to put this variable value, which is 3, into this expression for n. And what we have here is 2 multiplied by our 3 to the power of 2. 3 to the power of 2 gives us 9, and then when you multiply your 2 by 9, that gives you the maximum number in the n equals 3, or the principal quantum number 3, to be equal to 18 electrons. And this, when you look really in details, you realize that yes, when you have your s, your p, and your d orbitals, you know that your s orbital will have a maximum number of electrons to be 2, your p orbitals will have maximum number of electrons to be 6, so 2 plus 6 gives you 8, and then finally your d orbitals will have the maximum number of electrons to be 10. Therefore, we're going to have the total number of electrons to be, in this case, 18 electrons. So those, we'll talk about it in future videos. And this here is another style of question that involves math that you should be aware of when it comes to the atomic structure. Here is another question that says that given the subshell with an angular momentum of 3, what is the total electrons this can accommodate? And this here has a couple of keywords that we should keep in mind. First is the angular momentum, and this here in quantum is located as the second quantum number, which is expressed as the variable L. And here it says that L is equal to 3. So now the next point here is what is the total electrons that is in here, and based on this particular information for the angular momentum, the expression is equal to 4L plus 2. So that means if I multiply my L value by 4 and add 2 to that result, that will give me the maximum number of electrons that can be accommodated by this angular momentum. Therefore, by putting your value for L into this expression, which here in this case is 3, we multiply 3 by 4 and then add 2. That means that we get our value to be 12 plus 2. That gives you the total number of electrons to be what? 14, that can be accommodated at the L equals 3. Now, let's look at this in terms of how it looks like energetically speaking. So, in terms of a couple of laws we'll talk about in the future, the L value increases in terms of the energy, and what we realize is that when we start with the L value to be equal to 0, that is the minimum value that it can be at. This here is represented as the S shell, which has one sub shell. So this here leads us to the 1, which represents our p orbitals, which are the lobes, and this here will have 3 subshells, which are all suborbitals, which in this case are all containing 2 on each sub levels, and therefore that means you have a total of 6 electrons. When you get to the number 2, which represents the d orbital, this will accommodate 10 in total based on the number of electrons. And finally here for our target question here, which is our L to be equal to 3, is going to have 7 sub levels, and these sub levels are sub shells, which are all going to be focusing mainly on the orientation. And this here indeed is going to have the total number of electrons to be what? 14. So we're going to have 2 on each sub level. And so these here are how we are able to address angular momentum, just focusing mainly on the maximum number of electrons that is possible. Remember this key equation or expression to be able to accomplish this particular question here. Here we're going to look at another question, and this question is in the form of the following, which says how many electrons are in the 3d orbital if and only if the element's atomic number is 27. So just ignore that we are looking at a specific element by looking at the periodic table, and just say assume it could be any atom or another ion that we are going to be looking at here. And this here is going to be focusing mainly on the terms to be aware of, which is the element's atomic number. We know the atomic number here is what? The number of protons, and the number of protons can and must be for a neutral atom or element. In this case, it must be equal to the number of what? Electrons. And in this case, the number of electrons indeed based on this question here is 27. And so once we have this crucial idea in here, the next step is how do we relate this number of electrons here to the orbital, in this case the 3d orbitals. And this is where a particular principle comes handy, which is called the half-walls principle. And this here looks at a specific rule, which is the n plus L rule. Now this comes in 2 forms. The first form is that we must go from the lowest n to the highest n in terms of the filling up of electrons, and the next and most important point is that the sum of the n and the L must be given based on the smallest value, and the smallest value is what we are going to fill up first in terms of the number of electrons before we move to the higher n plus l value. And so that is how this here is set up based on the half force principle. And so let's look now at the third criteria here that involves the maximum number of electrons by connecting it to the number of electrons for this atom, or in this particular case, yes, neutral atom here, which is 27. So the maximum number of electrons based on the first principal quantum number, which is 2n to the power of 2, says that yes, for n equals 1 we have our number of maximum to be 2 electrons, and then for n equals 2 the maximum number of electrons will be 8. Now here is the little kicker here, which is for the n equals 3 and n equals 4, there is a specific assumption that we're going to be making between this particular space here based on the angular momentum when you combine it with the principal quantum number, which is a half force rule. And this here we have to distribute the electrons, which are in this case 17 electrons. We have to distribute within the 3 and the 4 shells, which contains those orbitals. And so let's look at the energies here to see how that lines up with the half force principle. In here we have what the following, where we're going to first focus on the 1s, and next is the 2s, followed by the 2p, and then the 3s, then followed by the 3p, and then next is the 4s, and finally is the 3d. And so once we have those taken care of, we can now move on to the next step, which is the adding of the electrons, or the filling up of electrons here. And what we state here that the 1s first, followed by the 2s and the 2p's, we're going to have 2, 2 and 6 respectively. And then moving on to the next part, which is the n equals 3 and later to n equals 4. This is where the assumption comes into play based on the half force principle. And so first here is our 3s is lower in energy, therefore we're going to fill that up. Then the 3p, which has 6 electrons maximum to be filled out, and that means that we're going to move on to the 4s, where we're going to pair up those electrons. That means we're going to have those 2 electrons, and we have 7 electrons left to be distributed around the 3d. And this here shows that once you unpair all the electrons in each orbital, we then pair up the other 2 orbitals here, and that leaves us with 3 unpaired orbitals there. So therefore we have our 3d orbital for the element atomic number 27 to have the 3d amount of number of electrons here to be equal to 7 when you count what you have right here. So this here is the final answer to this question, which requires pretty much 4 steps to accomplish this particular answer. And that is about it concerning all the types of questions that you should be exposed to when it comes to the atomic structure, not only being able to understand how to count electrons from a neutral atom to an ion, but also determining the maximum number of electrons given the principal quantum number, to next being able to determine the maximum number of electrons given the angular momentum, and then finally here is being able to determine how many electrons are in a specific orbital based on the half-force principle in collaboration with the n plus l rule. So hope you found this really informative. On our next video we'll look at big numbers in terms of atomic structure, but this time not with electrons but with what? Energies. So see you on the next one. Stay smart as always and believe in yourselves.